Good morning, Year 10. This is your whole class feedback for the Week 2 tasks that you have completed. Up here in the top left, you can see some of the common issues that I have come across when I've been marking your work. Please note that I will flag these as we're going through the Consolidate Dirt activity. So if you'd like to spend some time now, pause the video and go and see if any of these actually apply to you. Alternatively, we'll carry straight on. In the bottom left, under Actions, it will tell you what you need to do. First of all, everyone should attempt the Consolidate activity. It's just a way of assessing your progress before you jump into the other activities. This video is going up on YouTube, so all you need to do is to watch the video with your work in front of you and assess, correct, and improve your answers. In Teams, I'll provide timestamps so you can skip to questions that you had specific difficulty on. Under the Actions in the bottom left, it tells us what we need to be doing. So, if, for example, I got 4 out of 8 on question 1, that's below 5 out of 8, I'd go and use Seneca to revise topic 5.2.2 resultant forces. If I got 6 out of 8, however, I'd skip that and go on to the next one. The dirt activities you'll be doing after you've done the Consolidate will depend on exactly what you've got on each question. The Develop activity is there to test whether or not we can design an experiment. It's not testing our understanding of the science, it's just testing our understanding of how to carry out an experiment. The Stretch activity is there for those of us who want to get a bit further ahead and who want to understand a little bit more about how changing resultant forces affects the motion of an object. We will be starting this topic as a whole class, so even if you don't do the Stretch activity now, you will be able to do it in future. Question 1. Question 1 touches on the topic of upthrust and buoyancy, but we don't have to have a full understanding of that topic to be able to answer this question. Which block has the smallest weight? Almost everyone got this correct, just from their intuition. Block C has the smallest weight because it requires the smallest upthrust from the water to keep it floating. Figure 2 is not particularly useful. Sometimes you'll find figures like this in exam papers that don't really tell us any extra information that we don't already have. Question 1b is an example of a question where you are given an equation and expected to use it. Weight is mass times gravitational field strength. We should underline the values that have been given to us in the question, and we should also check that the units are correct. In this case, 2.5 kgs, that is the correct unit, and 9.8 newtons per kilogram, that is also the correct unit. So to perform this calculation, we just need to multiply 2.5 times 9.8. If we can do that in our head, fantastic, but my recommendation would be always use a calculator. Is 24.5. Check that you have not been asked to give the unit. In this case, it's actually already given to us on the answer line, so we don't need to separately write in newtons if we're filling this out by hand. Question 1c. It's important to read the question carefully and consider the situation carefully. When thrown into the water, the lifebuoy floats. The two forces acting on the lifebuoy are the weight of the lifebuoy downwards and the upthrust upwards. How big is the upthrust compared to the weight? The key idea here is that it is floating. It is not accelerating. That means that the resultant force must be zero, so therefore the upthrust is the same as the weight. Question 1D and 1E. Question 1D is an equation recall question. You need to be able to recall all of the equations from your GCSE physics when it comes to the real exam. I recommend using the app 23 Equations to constantly practice all of these equations over the next year. One of the papers from last year had nearly 50% of the marks available for math skills and recalling and using equations. So that meant that you could very nearly get a 6 without knowing any physics at all. The flip side of that is that if you don't recall any equations, then you need to get almost perfect answers for everything else in order to get a 6. The equation which links acceleration, mass, and resultant force is Newton's second law. F equals ma. Force is equal to mass times acceleration. Many people here wrote resultant force, which is absolutely fine, and is a good example of using the information given to you in the question to come up with an answer. Question 1E is a calculation question. If you got question 1D correct, then you're guaranteed almost to get at least 1 mark in question 1E. Please make sure that you underline any values that have been given to you, check your units, and then substitute the numbers into the equation before rearranging. That step is worth a mark. Then rearrange to get your final answer. So, as an example, force is 4.0, that is equal to mass, which is 2.5, these units are correct, multiplied by acceleration. That is a mark right there. Once you have done that, you can then rearrange the equation. I need to make acceleration the subject of this equation, so it needs to be on its own on one side of the equation. It's currently multiplied by 2.5. If I divide both sides of the equation by 2.5, then the 2.5 will cancel out. We should then use a calculator to get our final result. Our final result is that acceleration is equal to 1.6. Question 2. Question 2 starts out with another fairly useless diagram. However, it does have important information. The child and the pogo stick are not moving. That will help us answer some of the questions later on. Whenever you see the idea of two forces being equal, this is likely to be an example of Newton's third law of motion. The force exerted by one object on another is equal in magnitude but opposite in direction to the force exerted by the second object on the first. A compressed spring stores elastic potential energy. Whether we're talking about a spring or a marshmallow or a gummy, anything that can be elastically deformed is storing elastic potential energy. Anything squashed, stretched, or bent. Question 1C. We've been given a weight and a gravitational field strength. we need to calculate the mass of the child. Now, the question to write down the equation we've already had today, so we'll skip over it for now. But remember, you need to put the numbers in before rearranging the equation. So weight is 343, and that is equal to mass, which we're trying to find out, multiplied by gravitational field strength, which is given to us as 9.8. At A level, that will be 9.81. At GCSE, it has been given as 10 before. Use whatever the question says to use. Once we've got those in there, we now need to rearrange. We need to make mass the subject. So, again, similarly to before, if we divide both sides of the equation by 9.8, then it will cancel out on the right-hand side. We'll be left with mass on its own. Again, always use a calculator to perform these calculations. Don't try and do them in your heads. It is going to come out as a nice round number, which is one way that we can be more confident that our answer is correct. Question 2e and 2f. Question 2e is about Hooke's law. We need to be able to recall this. It's another one of these equations that we need to know. Normally, we talk about extension. When we take a spring and we pull it apart so the rings separate. And that's the experiment that we did. But Hooke's law also works when you compress, when you squash something as well. So whenever we use the word extension, then compression could be used instead. So the equation was force is equal to spring constant times extension. In this case, we can always just put in compression instead of extension. When we've got this, we can start to use the equation to calculate our spring constant. But it's important to realize that 30 centimeters and 23 centimeters are both lengths. They don't appear in this equation. The extension of a spring, or the compression of a spring, is the difference between the original length and the new length. So in this case, there's a mark for saying that the compression is equal to 30 minus 23. So it's been compressed by 7 centimeters. Earlier on in the question, it gave us the force as 343 newtons, the weight of the child. So we should write that down there to make it very obvious. 343 newtons. Now we have enough information to substitute the numbers in. 343 newtons is equal to the spring constant multiplied by 7 centimeters. Now, there is one additional problem here. It wants the answer for spring constant in newtons per meter. And that means we're going to have to put newtons and meters in. So this centimeters needs to be converted into meters. Hopefully you remember that there are 100 centimeters in a meter. So there is 7 divided by 100 meters in 7 centimeters. If I tried this the way around and I thought that maybe I needed to multiply by 100, I need to think very carefully. Is 7 centimeters the same as 700 meters? Clearly not. So I know that I'm getting this the right way around when I divide by 100. And our answer is 0.07 meters. Now that we've done this, we can finally rearrange. So my spring constant is equal to 343 divided by 0.07. As ever, I need to go to a calculator to work out the answer. And I get 4,900 exactly. To understand the difference and similarity between extension and compression, this simulation, which is available at the URL at the top, is a really good way to test your understanding. Have a look at it if you're having difficulty with some of this Hooke's law material. Question 3. The center of mass of an object, when the object is a regular shape, is going to be at the center of the volume of the object. So on a ruler, you're going to be halfway between the beginning and the end, so that's on the 50 centimeter mark, and if we're being precise, it'll be halfway along the width of the ruler. So somewhere near where my mouse cursor is now, somewhere in here. The mark scheme just wanted anywhere along the 50 centimeter line though. There were a number of good answers for 3AII, the definition of a center of mass. The easiest way to say it though is that it's the point at which the mass of the object can be thought to be concentrated. So the weight of the object acts from that point. It's the point that it can balance above is absolutely fine. Question 3b is a how science works question. We have not done this experiment. You are not expected to know anything about this specific experiment. All of the information you need is in the question. The student taped a 100-gram mass to a meter rule and set up the apparatus as shown in diagram 2. She suspended the meter rule from a nail through a hole close to one end so she could use the meter rule as a pendulum. The distance d is the distance between the nail and the 100-gram mass. So that's setting up the experiment. When later on you're asked to explain how to use the apparatus, you won't get marks for repeating that information. You need to include information that you yourself are coming up with. Draw on diagram 2 a Y to show the possible position of the center of mass of the pendulum. This is quite a tough question. We need to think that there are actually two objects here. There's the mass and the meter rule. So the mass has its center of mass here. The meter rule has its center of mass around here. So that means that the center of mass of the whole pendulum has to be between there and there. So somewhere around here. Many people didn't get this because they marked the center of the mass. Unfortunately, the meter rule also has mass. Complicated question. This next part is just about data manipulation. So you're being asked to complete the table. As it says there, you may use the space below to show you're working. It doesn't mean that you have to. We need to calculate the mean value for 10 swings at 70 centimeters. So you need to add these numbers together and then divide by 3. You should quote it to 3 significant figures. So actually the answer is still 16.5. When you put it into a calculator, you'll get out 16.533, recurring, but round the answer. Some people got this last bit wrong. We're trying to average these values up here. But if we look at what this column actually is, it's the mean time for one swing. You get this by just dividing the mean value for 10 swings by 10. So it's just 1.65. Much simpler than some people were making this out to be. For this part of the question, you need to describe how to use the equipment that you have already been provided with, and suggest what other apparatus will be required. Instead of going through and giving you my answer, I'm going to show you the mark scheme directly. That way you can see exactly what's required to get a high mark on this question. The mark scheme will also provide some structure for you when you're answering the develop question. So this is the mark scheme that examiners see. So first of all, it's marked according to a best fit principle. Is your method valid? Will it produce the results expected? And have you followed all of the instructions exactly? To get a high level of marks, you need to have a clear and detailed description of the experiment. You need to mention a safety factor, and you need to talk about uncertainty. In this context, uncertainty is about either making it a fair test or improving accuracy. So, you were suggested to include additional apparatus, and there was no way to actually measure time in the apparatus given to you. So, just mentioning that you need a stopwatch is going to contribute towards your answer. How are you going to ensure that you get the data from the question? Well, you're going to have to time how long it takes for 10 swings. You're going to measure from the hole to the center of the mass along the meter rule. You then need to say that you're going to change something. You need to have identified your independent variable. In this case, that's the position of the mass. In order to keep something a fair test, you have to make sure that it is the independent variable that's affecting the dependent variable. It's basically asking, how are you going to keep the control variables the same? So you need to make sure that you're timing from the same point on the swing. You need to make sure that you are lifting it to roughly the same distance. Your risk assessment needs to be relevant. In this case, there's a few options available. The most likely thing here is that the stand will topple over, so you should use a clamp to secure it to the desk. And then finally, how are you going to improve accuracy? Well, you're going to discard anomalous results. You're going to take a larger number of values than those that have been given to you so far. You could use something called a fiducial marker. This is a concept we use at A-level a lot. It's just a mark, something for your eye to focus on, so that you can make a decision about when it gets to the top of a swing, for example. This next question is about describing results, and there were some fairly vague answers going on here. The important thing to remember is that you can use the labels on the axes to describe the pattern that you see. This is 2 marks. You've been given 4 lines to fill. So there's probably 2 different things that we're going to be able to say. When we look at this line, we can see that clearly it's divided into 2 different patterns. There'll be 1 mark for describing each. How I would answer this, I'd say as whatever appears on the x-axis increases, and then I describe what happens to the y-axis. So we'll start off describing the first part of this graph. Use numbers that have been given to you. You don't always have to do this, but it's a good habit to be in. So between 10 and 30 centimeters, as distance d in centimeters increases, time for 1 swing in seconds decreases. That's us describing this part of the graph here. For my second mark, I now need to describe the part of the graph here. However is a good word to use when you have a change in the pattern that you see. Above 30 centimeters. The time for one swing in seconds increases. And then optionally, you might want to use some data here. Up to a maximum of 1.80 seconds at 90 centimeters. That last part is not scoring, is not required in this case. But if it was a 3-mark question, would be worth extra marks. The next question is about anomalies. Would you consider any of these measurements to be anomalous? Everyone that I've seen so far has got this correct. None of these measurements are anomalous. How do we know that? Well, because they're all close to the mean, and because the range, the difference between the smallest and the largest measurement, is very small. I would answer this something along the lines of, no, the range is only 0.2 seconds, and all measurements are close to the mean value. Question 4. The resultant force we need to calculate by taking away the smaller force from the larger force, because they're acting in opposite directions. So the resultant force will be 4 newtons to the right. Another way of thinking about this is to say that forces in opposite directions cancel out. Question 4b is about base jumping. Again, there's context to these questions that will always be new, that you won't have come across. But it'll be asking very similar questions each time. You have 4 forces labelled A, B, C, D. When will the base jumper accelerate? The base jumper will accelerate forwards when there is a resultant force in the forwards direction. So for there to be a resultant force in the forwards direction, force A must be bigger than force B. The base jumper falls with constant speed when there is no resultant force in the vertical direction. So that must mean that C and D perfectly cancel out. So force C is equal to force D. Generally speaking, this was a well-answered question. This next part actually looks ahead a little bit to some stuff that we haven't really covered yet. But lots of people managed to get the right idea. Opening a parachute will reduce the speed of a falling base jumper. That's kind of something we can get from intuition. That's why parachutes exist. But why? Lots of people didn't get the wording quite right here. Opening a parachute increases air resistance, which increases the upwards vertical force. This means that there is a resultant force upwards. Which will cause a deceleration or an acceleration upwards. Question 5. Draw only 3 lines. Some people found this demanding, possibly because if you edited this in Word Online, the answer boxes were not on the same page. So apologies for that. But the first one, A, is actually really important. In this case, we have 500 newtons forwards and 500 newtons backwards. So that means that there's no resultant force. The principle of inertia means that it carries on in the same state of motion. So it cannot be slowing down or accelerating forwards. However, we now have a choice between stationary or constant speed. And they both could be true if the car is currently stationary or moving. Now, because there is a backwards resistive force due to friction and air resistance, that means the car must be moving. So it is not stationary, it will move at a constant speed. A, constant speed. B, there is a resultant force in the forwards direction, so it's accelerating forwards. C, there is a resultant force in the backwards direction, so it is slowing down. What direction does the force that the car exerts on the barrier act? Well, the barrier is being pushed to the right. The barrier must exert a force on the car to the left because the car is decelerating. Question 3. The car exerts a force of 5,000 newtons on the barrier. The force exerted by the barrier on the car will be equal to 5,000 newtons. The reason for this is that it's Newton's third law. Even if the barrier did move, it would still be true. And finally, the last question. Why would you attach electronic sensors to the dummy? Well, measuring the speed of the car just before the impact can be done from the outside. Measuring the distance the car travels during impact can be done from the outside. It's much more likely to be measuring the forces exerted